In this section, we're going to be talking about different methods for data visualization and also some of the errors that we might encounter or pitfalls in trying to visualize certain types of data. First, we're going to talk about how we visualize qualitative data. So here we're not looking at numerical data, although of course we're going to need to convert the data into numbers in order to be able to visualize it in a graph to begin with. So when I'm talking about qualitative data, the type of qualitative data that we're really able to use data visualization techniques for is going to be frequencies. Um, and this means that we're going to be using a particular form of qualitative data. We're going to be using categorical data or nominal data in order to use these methods that we're going to be talking about in a minute. So most of the time, our qualitative data, our categories or our nominal categories, these are going to be set up initially in what is known as a frequency table. And from there, we can use several techniques to kind of chart out or visualize the table. But the table itself is sort of our most primitive or basic form of data visualization for frequencies. So here we've got a breakdown of the beverage that people drink most in the morning. So we can see that of the 50 people who were sampled, 22 of them drank coffee in the morning, 10 had tea, 7 had energy drinks, 8 had soda, and 3 didn't drink anything, any caffeinated beverage in the morning. Um, so, yeah, I mean, you can kind of get an idea of what all of this looks like. We can kind of calculate percentages if we would like to calculate the percentage in a frequency table. All we've got to do is take the number in any particular category, the frequency in that category, and divide it by all of the individuals who were sampled. So 22 divided by 50 is 44% of people drank coffee. 10 divided by 50, 20% of individuals drink tea, etc. All right. So, and again, this is our most basic way of visualizing data. You can kind of picture, especially for a simpler data set like this, you can kind of picture what those frequencies might look like just from looking at a frequency table. This is our first method. The next method of visualization for categorical data is a pie chart. Pie charts are really nice for looking at relative proportions or proportions relative to the whole. So you can see that this is in this pie chart exactly the same data that we had last time. So we've got 44% of people drinking coffee, 14% drinking energy drinks, 20% drinking tea, 16% drinking soda, 6% drinking no caffeinated beverage in the morning. So again, same data from earlier, just depicted in a way that where we can kind of see, okay, we can just see how much of an influence um, coffee seems to, to have relative to everything else in our pie chart. We can see how that larger proportion looks compared to the whole and to those other categories. And it's easier to kind of visualize, when something is double or when it's a majority or a plurality. We can pretty easily see that coffee drinkers are, they're the biggest category, but we can see that they're not quite a majority. To be a majority, they'd have to take up more than half of the pie chart. Again, we don't really get any new information depicting things this way, but at a glance it is a little bit easier to kind of see that frequency data looking at this pie chart compared to just looking at the frequency table. We also don't lose, well, we lose a little bit of information actually in the pie chart. We could add it in. I mean, we could do like, n equals 22 here in addition to the 44%, so we don't lose any data. But as depicted right here, yeah, we do lose those counts within the frequencies, the way that we've kind of pulled it out here. And usually with a pie chart, we do lose. We can do the math and we can figure out how many people are in each category as long as we know how many people overall there are. But yeah, we do lose a little bit of information potentially in a pie chart. Pie charts also don't work terribly well if we have lots of categories. So you can imagine if we had, 20 different options here, it becomes really difficult to see very, narrow slices of the pie, right? It just becomes harder to kind of pick apart. In all fairness, a frequency table is also kind of hard to see everything if there's 20 or 30 different options, but a pie chart definitely doesn't work terribly well for that. And pie charts always make it kind of look like we've got more observations because we have the whole represented, and we don't necessarily pay attention to the count within the whole, if that makes sense. So 6% and none, that somehow seems like more than the actual three people who are in that category. So when people just kind of look at pie charts, often they feel like there's more individuals in each one of those slices than there really are. The next option we have gets around some of those issues we mentioned earlier. This is a bar chart. So in bar charts, we set them up in a pretty specific way. They always have to be set up this way. So on the y-axis of the chart, we're always going to have the frequency, the count. And on the x-axis, we'll always have our categories listed out, and our boxes themselves, the bars themselves, should always have a little bit of room between them. That helps represent that these are distinct categories that we're looking at. Yeah, and bar charts again. This is the same type of information. Again, we can see, all right, we got 22 people in this category, 10 people over here, 7 here, 8 here. Right, so it again places the emphasis on counts rather than percentages. It still allows us to quickly kind of visually compare our different categories and quickly see, when something is double, so we can, easily see that, coffee drinkers are more than double the frequency of tea drinkers. We can kind of easily see that these three categories are pretty comparable. All of that's very easy to see just at a glance. And even though, because of the simplicity of a bar chart, we might be tempted to add a whole bunch of embellishments and graphics and different information, generally speaking, we shouldn't really do that, right? We should keep things nice and clean and simple. Allows us to quickly communicate information. Bar charts also have an added benefit that we can pretty easily represent two different comparative data sets using a bar chart in a way that it's harder to do with a frequency table because we'd have to just have two different frequency tables. And it's harder to do in a pie chart as well. We'd have to have two separate pies in order to do this. And neither of them lend themselves to comparison as easily as bar charts. Bar charts really shine when we're trying to compare two different categories. So here we can see we've kind of expanded our data. We've got morning and evening drinks. And so we can kind of just compare. We can say, all right, in the morning, people prefer coffee. We already know that. But in the evening, it seems like people prefer not to drink caffeinated beverages. Tea is still a popular beverage in the evening, followed by soda. We should really have the ends here so that we can see how many people are in this one, but we can retrace our steps fairly easily, and we can see what this is. Well, that's a terrible line. You see what I mean? This is about 6 people right here. Anyway, we should always top our bars with the actual counts, though that is better. But comparisons here, you can see how easy it is to add that second data set. We could even add a third data set. We could have a morning, midday, and evening drinks. And, bar charts facilitate that sort of comparison across two or more different data sets quite easily. So we mentioned that we're better off keeping bar charts relatively simple. Well, let's go ahead and talk about a couple of other common errors that we see. So one of the most frequent errors that we will often see with bar charts is one that's often meant to be kind of deceptive, and this is not using zero as the base of the bar chart. Right. So when we do that, what it basically does is it'll make our largest category appear even larger relative to our other categories, because basically what we're doing is we're slicing off a chunk of the bottom from our other categories. So in this particular case, we've got, all right, how many people are switching to Mac computers. And we've got, okay, so people who are switching from a Mac to none, people who are switching from Windows to Mac. people who are switching from Mac to Mac. And over here, we've got again, none, Windows, Mac to Mac. Um, this particular chart over here on the right-hand side, it makes it seem like not a lot of people are switching from Windows to Mac, right? It kind of makes that look a lot smaller. We can technically still see the same information, and it's that I would say around 60 people have switched from a Windows to a Mac computer. But the second graph definitely makes it, or second chart definitely makes it seem like fewer people. It shrinks the size of that bar. So it doesn't seem like quite as many people are making that switch because we start at 50 rather than starting at zero. And so in that case, if we were, for example, working at Microsoft and we wanted to convince a CEO or somebody else that they shouldn't really be concerned about users switching to Mac computers, we can say, oh yeah, most Mac users are switching from Macs to Macs. We're not really losing a lot of Windows users. Technically true. I mean, that's what we talked about earlier. When it comes to sort of deceptive practices in statistics, we're often dealing with things that are technically true, but the way we're displaying the information kind of pushes people towards a particular interpretation. So we could see how this could certainly be done in this case if we wanted to make people less concerned about that middle category. Another common error that we see in bar charts is trying to be too graphically flashy. And so here you can see that somebody has tried to add different graphics for our beverages instead of just using bars. And of course, this is on purpose, kind of a particularly messy and egregious example. But there are certainly less messy ways of doing this as well that would look a little bit better, but still, generally speaking, just sort of obscure information that we need to know. It makes it harder to kind of see where the top of the bar is and where the bottom of the bar is. Sometimes the graphics themselves are a little bit hard to interpret, like, what exactly do these three bars or graphics represent? It's not 100% clear. We'd probably need to include a key. And that just kind of makes it more difficult to interpret the information that we're trying to convey, right? Um, that's the issue really at hand. So, other things to keep in mind for bar charts, obviously we shouldn't use graphics like this. We do need to make our bars different colors. That's typically helpful. Although sometimes it's helpful to do colors and textures. That makes it a little bit more accessible. So, for example, if you've got a red bar and a green bar, but you're showing this and you maybe don't know that somebody in your audience is red green colorblind, they might have a hard time telling those two colors apart. So often making things colored and textured can help. And what I mean by textured is you can have, or patterned, I guess is a more accurate word. So when you're drawing out your bars, maybe one of them has lines and the other's got checkers. Drawing is terrible, but you can kind of see what I mean. A technique like that can be potentially even more readable than you can have a solid bar and a clear bar, right? Things like that make it a little bit easier to easily communicate information. That's ultimately what we're trying to do in a bar chart is just make quickly looking at the data and visualizing it and understanding it. We're trying to just make that process easier. Now, one more kind of chart to talk about before we move on from qualitative data is a line chart. And generally speaking, line charts are not terribly recommended, even though they're very easy to produce if we already have the bar chart. And so you can imagine, I mean, here was our bar. And if instead of drawing an entire bar, we just sort of placed a dot at the top of the frequency, we would have these dots, and dots themselves are kind of hard to see in the absence of bars, so we might be tempted to kind of draw lines between them to emphasize the pattern. Now, the problem with line charts for categorical data like this is that it does seem to suggest a connection between the different categories. And remember, we said we want to make sure that people know that the categories are separate and that they're not connected. So that's kind of a little bit inherently misleading or problematic that we're making those connections between our categories. Also, depending on the order that we put things, if we put our categories in order of ascending frequency. We could make it look like we have some sort of upward trend. If we put them in order from descending frequency, which is how they're ordered here, we kind of look like there's a downward trend because people are used to reading left to right. And so again, we're sort of like giving the implication of change over time or trend lines where we don't really mean to do that because categories, of course, don't have trends or connections or change over time. So we probably want to avoid line charts for these types of data and just stick to the pie chart. If we just kind of want to look at proportions and stick to the bar chart, especially if we're trying to do comparisons. All right, so we're going to go ahead and switch over to talking about how we depict quantitative data. So remember, when we're looking at qualitative data, we don't really care about order or measurement, right? If we're looking at nominal categories, they don't have an order. We're not measuring anything. We're just counting how many things go in each bucket. And the different categories we have, those are just the different buckets. So frequency tables, they tell us about how often something drops in the bucket, but they don't tell us what order the bucket should go in or whether a bucket is better or higher or lower. Just as a reminder, qualitative examples are things like movie genres are qualitative, genders are qualitative, birth cities, cities that you were born in, your favorite food or drinks, all of these are qualitative. Quantitative would include things like rankings, populations, calories, caffeine content, stuff like that would all be examples of quantitative information. So for our quantitative examples, here we're going to start off with GPAs. So once again, we start off with just a table that is a list of our data. So each data point in this data set represents somebody's high school or college grade point average. So we can see that this person down here has a GPA of 0.5. So pretty low. This person over here has got a 2.4 GPA, definitely better. This person up here has a 4.0 GPA. That's as high as you can get. Here's a 3.9. Right, that's what we're looking at here. So we did lay out these data in ascending order. You don't necessarily need to do that, but for the purposes of visualizing the data and creating those visualizations, does make life a little bit easier if they are laid out this way. But here again, we can, if we want to kind of know, okay, what GPAs do people have? What's a typical GPA for individuals in our data set? Technically, we can stare at this table a pretty long time and we can start to glean information, right? We can see, all right, very few people have a 0 point something GPA. There's a handful of people with 1 point something GPAs. There's a lot more people with 2 point somethings. It looks like the 3 point somethings are the most common category, and there's relatively few people with the 4.0 GPA. So looking at the data, we can sort of start to pull information out of it, but it is difficult to kind of tease information out of just a table like this. So obviously we want a different way of representing this information that might be a little bit more useful. So our first option for depicting data in a slightly more visually appealing and interpretable way is what is called a stem and leaf display. So here, basically what we're going to do is we're going to take each one of these numbers. GPAs, turns out, are pretty easy to do this with. We're going to take the number before our decimal point. We're going to place it right here. And we're going to take the number after our decimal point, and we're just going to list them out, right? So we've got one person who's a 0.5, one person who's a 1.2, one who's a 1.6, one who's a 1.8. Then we've got somebody with a 2.0, someone with a 2.1, somebody with a 2.3, etc. Right? That's basically how we've laid out these data. For a stem and leaf display to work, obviously we need at least two numbers, right? We need at least two figures in order to do that. It can be a decimal. A decimal's a pretty easy place to kind of draw that, but you can imagine that if we just had numbers ranging from, 5 to 99, it would be pretty easy to set this up as well, where we could put the number in the tens place on the left-hand side, and we could put the number in the ones place on the right-hand side. So we don't just have to represent decimal data this way. We can really easily represent anything where we've got, at least two digits. We really do need, ideally, two digits for the stem and leaf display. Once we get into, three or four digits, it works a lot less. It can still potentially work, but really with, any data where we've got two digits, that's really where things are ideal for this particular type of system. And you can definitely see that the stem and leaf display adds a lot of information. So now we can very easily see that the majority of our students have GPAs in the 3 point something range, relatively few in the 4 point or 0 point or 1 point something. And then the second most common category, it almost creates a little bar chart that is going from our left to right rather than up and down vertically. So interesting and useful technique for visualizing some types of data. You can also imagine a situation where maybe we just have a lot of individuals in certain categories, like maybe we have a lot of people in the 2.0 or the 3.0 category, and so we want to kind of split things out further. So here's how we would go about doing that, right? Where we might, um, instead of including just one category for our first digit, we include two. So people who are five or below and people who are above five, right? People who are 2.0 to 4, people who are 2.5 to 9. And doing this creates a little bit more of a clearer distinction within those larger categories. We can kind of see, okay, people are pretty much evenly split between high 3 point something GPAs and low 3 point something GPAs, and same for two. It just provides a little bit more nuance in our data visualization to do it this way. So we can choose to, if we would like, kind of split things into high and lows for each of our leading numbers on the left-hand side. Stem and leaf displays also do allow us to do some comparison. So in order to do a comparative stem and leaf display, we can put our leading numbers, in this case still the number before the decimal, in a GPA. We can put it down a center column, and we can have 1 year over here and 1 year over here. So very two different data sets. Over here, we've got the 2020 students. Over here, we've got the 2021 students, and same number of students, same number of GPAs. We're just comparing two groups of individuals. So here we've got in 2020, somebody was a 0.5 and a 0.7. Here, somebody was a 1.0 and a 1.1. And over here in 2021, here's somebody with a 1.6 and a 1.8. So we can just kind of see how we're setting up those two different years. And then once we've got all of that set up, we can very easily do a quick comparison. And we can see, for example, oh, it certainly seems like, GPAs were a lot lower in 2020 than they were in 2021. We didn't have anybody with a 4.0 in 2020, but in 2021, we had several people with 4.0s. Most of our students have 2 point somethings or 1 point somethings in 2020. Most of our students have 3 point somethings in 2021. So this is called a back-to-back stem and leaf display, and it's good for quickly being able to compare two different data sets, where otherwise you'd have to kind of flip back and forth between different tables. Of course, we kind of gave an ideal example for a stem and leaf display, right? GPAs, especially a GPA with, just two digits, that works really well for the system. When we start getting into negative numbers For example, stem and leaf displays work a little bit less. You can imagine it's a little more challenging to represent negative numbers, although your textbook should have some examples of what that might look like in a stem and leaf display, but it's a little bit less intuitive once we've added negative numbers. It also works pretty well for positive whole numbers or um, decimal numbers without very many decimal places. Once we've got a lot of decimal places, things don't work quite as well. When we have many more than 2 digits, or we really need the more precise decimal points written out to, 2 or 3 or 4 different decimal places, that's where we really kind of have to avoid using the stem and leaf displays anymore. Additionally, stem and leaf displays tend to work best when we don't have a ton of observations. So usually we want to use these for data sets with around 100 observations. Once we get above about 200 observations, it really doesn't, it becomes too cluttered to be good data visualization. So they work best if we're dealing with, 100-ish plus or minus 20 or 30 observations. When we have far too few observations, it doesn't really accomplish much. You can imagine if we're only looking at 10 GPAs, the stem and leaf display doesn't really add much information. And similarly, if we're looking at 500 GPAs, the stem and leaf would be basically uninterpretable too, because there'd just be too much data crammed into it. When we have much larger data sets, for example, maybe a data set with 500 individuals, often what we're going to want to do is set up a histogram instead. So a histogram basically just it tells us it's a good way of kind of showing the overall shape of a distribution when we have a ton of data. So here we can see, all right, we've got students' ACT scores. So just as a little bit of a extra information here, ACT scores vary from about 1 to 36, with the average score for an ACT being 19.4 in the US. And so here we've got some ACT data. We've got 500 students, ACT scores. We can see we set this up as kind of a upper and lower limit buckets. So here we've got, people with a 15 or a 16 on their ACT. So the way we've kind of represented it. Oh, sorry, right there, but that's a 15 or a 16. Here we've got people with 17s and 18s. In this bucket, we've got people who have 19s or 20s, etc., all the way up to people who have 35 or 36 on their ACT. What we can do is we can take these data and we can chart it out into really a bar chart, essentially, is what we're doing. With a histogram, our bars are all going to touch because here we're looking at frequencies that kind of are connected in a way that our nominal categories are not. So here is that same information represented as a histogram. So again, you can see if you compare this to just the frequency table up here with our upper and lower limits, this is very easy to kind of see what's going on here. We've got our frequencies on the y-axis, just like we did for bar charts. You can see we don't have categories over here. Instead, we've just got our number range. And so here we probably should go ahead and label these. I don't know why they're unlabeled, but we should have those labeled out according to the buckets over here, right? So this is our 15 through 16 individuals. These are our 16 and 17 individuals. We can see that most people, the biggest group of individuals, are right here in this 27 or 28. It's a relatively high scoring group of individuals. And then we've got kind of this downward trend going off to the sides, relatively fewer people getting lower or higher scores. Most people are kind of right here in the middle. So histogram, it's a pretty nice, easy way of looking at the shape of our data. We can also see over here that this looks almost normally distributed. Right? In fact, it does kind of look normally distributed. It's a little bit lopsided, but mostly this probably would meet the criteria for being a normally distributed data set. As you might imagine, we can pretty easily just take out the bars. We could put dots where the top of the bars would be, and then just draw a line along those different dots of our histogram. And we'd end up with a polygon like this. This is called a frequency polygon. Um, Really, its main use is for comparing two different distributions, because it's kind of hard to overlay one histogram over another histogram, and looking at them side by side sometimes doesn't allow us the easiest comparison. So that's really where these are most useful. If we want to represent proportions, we can use the cumulative frequency polygon, shown here, where we kind of like fill up the distribution until we hit 100% of our individuals. Right here's where we hit 100%. For this sort of data, that wouldn't be terribly useful to do. But you can see that if I want to compare two different distributions, all of a sudden that frequency polygon is a lot more useful than trying to overlay one histogram on top of a histogram. Because the polygons are hollow, we can kind of easily see the point of comparison. So here we're looking at two different sets of ACT scores. We have the one that we were looking at earlier. These are our 2026 high school graduates, and over here are our 2024 high school graduates. If we had two different um, data sets like this, we could very easily create two different frequency polygons and just sort of overlay them so that we can easily compare where the peak of one is. So we can see in 2024, our students are peaking around a 20 for their score, so much closer to average. Over here, they're peaking around a 2026. We can see that we've got a lower low point on this one, and not as high of a high point on this one either. So we can kind of see those differences, visualize them very quickly, and make a quick comparison. So nothing really beats the frequency polygon where we're trying to compare two different quantitative data sets. The last option we're going to talk about today is something called a box and whiskers plot. This one's a little bit different because instead of charting out a frequency like we do for the histograms or for our various forms of depicting qualitative data, or just charting out the data like we do for the stem and leaf plot, in this case, what we're going to be doing is focusing on where data falls by percentile. So the way that a box and whisker plot works is, first of all, we have the box. The box itself is going to represent where the data fall from the first quartile to the third quartile. So basically, the middle 50% of data. Where does all of that end up? And then we've got the whiskers, which is going to tell us where the maximum value is and where the minimum value is, and how far away that is. How far the minimum is from the first quartile, how far the maximum is from the third quartile. We can also use the plot here to show where an outlier would be if we don't want to include that with our box and whiskers plot. We can depict mean as a dotted line. Sometimes it's also predicted as or shown as a plus sign, and median as a solid line. We have a lot of information that's depicted here. Box and whiskers plots are also really good for comparing different distributions, and we can kind of see how spread out data are fairly easily from this box and whiskers. If we've got a very small box, that means the data is not very spread out. If we've got a much longer box, that would mean that the data is very spread out. All right, let's go ahead and look at an example of how we can use the box and whiskers plot. So here we've got some data. You can notice that the data here, we've got two groups here. We've got sophomores, and then we've got their scores, and we've got juniors, and then we have the junior scores. So we're going to make two different box and whisker plots. We could make one combined, right? But we're going to make two different ones because this also shows how we can compare two different distributions. We're going to set these up kind of similarly to how we do for bar charts for qualitative data, for nominal data. We're going to have our values over here on the y-axis and our categories on the x-axis. So these are our two different distributions. So here we can see most of the data for our juniors, most of their scores. The majority of it is going to float between around 16 and 18. We can compare that over here with our sophomores, where their scores are more spread out and lower, between about 11 and 14. That's 12 and 14. So we can see the difference in spread, right? These data are more spread out than these data. We can see where the maximum number is. The max score is a 20. The minimum score down here for our juniors is around a 13. Meanwhile, the minimum score for our sophomores is a 10, and the maximum score is around an 18. So you can see that pretty easily. We can also see where the mean is. So the mean is around, looks like a 16 or 17. Obviously, adding numbers to this would help, but you kind of see how it's set up for the juniors and the sophomores. We've got a lower mean, maybe around 13 or 14 for our sophomores. The advantage of a box and whiskers plot is that it conveys a lot of information, right? So they're pretty informationally dense. We can get, if we set them up entirely, we can see outliers, we can see the minimum score, the maximum score, we can see where kind of the center of the data is, we can see how spread out the data tends to be, we can see the mean and the median all depicted visually, which is something we really don't get from any of those other methods that we've just talked about. The downside of the box and whiskers plot, though, is kind of that I just had to explain it in so much depth. The other techniques we went over, maybe stem and leaves aside, were, you could figure them out pretty easily. They were all pretty intuitive. The box and whiskers plot is not particularly intuitive. It does require, some information. It does kind of require that key to pick apart what each line and box actually represents. And because of that, if we're dealing with people who are familiar with data visualization, these can be great. But when we're dealing with an audience who may not be super familiar with data visualization, who hasn't seen a lot of these before, it kind of defeats the purpose of visualization. Visualization is generally supposed to make it easier to digest the information. Box and whiskers plots don't necessarily do that. All right, and that is pretty much it. You can see that normally I would have people kind of break out and do a little bit of discussion here. I'll ask that you just do this independently, just kind of take your own notes about this. So first of all, think about what the most important lessons are for data visualization. If you were maybe trying to explain to a friend who's got to graph some stuff for their company, maybe some qualitative data, maybe some quantitative data, how would you tell them to do that? What tips would you give them? And then also, think about ways in which we can use visualization or which other people might use visualization to kind of mislead or miscommunicate. Have you seen any examples of that? You probably have, but go ahead and just take a few minutes to think over those. Again, you can kind of add those to your notes. I'm not going to collect those in any way, but this is a good thought exercise to end on for this section.